for measuring vast cosmic distances. By studying these standard candles, astronomers have determined that the universe is expanding at an accelerating rate, leading to the discovery of dark energy, a mysterious force driving cosmic expansion. The study of supernovae is not just a matter of astronomical curiosity, it has practical implications for Earth. A supernova occurring within 50 light-years could pose a significant threat to our planet, stripping away the ozone layer and exposing life to lethal radiation. Fortunately, no nearby stars are currently on the verge of such an explosion. Supernovae also produce some of the most exotic objects in the cosmos. A core collapse event can result in the formation of a neutron star, an ultra-dense remnant where a sugar cube-sized piece of material would weigh as much as Mount Everest. Some neutron stars become pulsars, spinning rapidly and emitting beams of electromagnetic radiation. If the collapsing core is massive enough, it forms a black hole, an object with gravity so intense that not even light can escape. The first recorded supernova visible to the naked eye was observed by Chinese astronomers in 185 CE. Since then, historical records have documented several spectacular events, including the famous SN 1054, which created the Crab Nebula, and Kepler's supernova of 1604, which shone brightly for weeks. Today, astronomers use powerful telescopes like Hubble and the Vera C. Rubin Observatory to detect and study these cosmic detonations. Supernovae also generate powerful neutrino bursts, subatomic particles that barely interact with matter. The detection of neutrinos from SN 1987A in the Large Magellanic Cloud confirmed key theories about stellar collapse and provided rare direct observational data on the inner workings of a dying star. Some supernovae challenge our understanding of stellar physics. Hypernovae, for instance, are even more energetic than regular supernovae and may be linked to long-duration gamma-ray bursts, the most intense explosions in the universe. The nature of so-called superluminous supernovae, which shine 10 times brighter than ordinary supernovae, remains an active area of research. Another mystery is the fate of Betelgeuse, a red supergiant in the Orion constellation. This massive star is nearing the end of its life and could explode in the next few thousand years, or even tomorrow. If it does, it will be visible in broad daylight from Earth, offering humanity a front-row seat to one of the most extraordinary cosmic events. Supernovae not only illuminate the past but also shape the future of astrophysics. Scientists are using advanced simulations, high-energy observatories, and gravitational wave detectors to probe the secrets of these stellar cataclysms. Understanding supernovae could help answer fundamental questions about the nature of matter, the origins of elements, and the ultimate fate of the universe. The next nearby supernova could revolutionize our understanding of the cosmos. Telescopes worldwide are constantly scanning the sky, hoping to catch the next great stellar explosion in real time. When it happens, astronomers will be ready. Supernovae are also responsible for some of the most extreme and mysterious phenomena in the universe, including magnetars. Magnetars are highly magnetized neutron stars, with magnetic fields trillions of times stronger than Earth's. These bizarre remnants occasionally release powerful bursts of X-rays and gamma rays, capable of affecting our planet's upper atmosphere even from thousands of light-years away. The origin of magnetars is still debated, but many scientists believe they are born from the most energetic core collapse supernovae. Another intriguing class of stellar explosions is the so-called failed supernova. In these rare cases, a massive star collapses directly into a black hole without producing a visible explosion. Some astronomers have observed stars that seem to vanish without a trace, hinting that direct collapse black hole formation might be more common than previously thought. If confirmed, this could reshape our understanding of how black holes form and evolve. Supernovae are not only natural laboratories for studying high-energy physics, but they also play a role in shaping entire galaxies. When a supernova explodes, it injects vast amounts of energy into the surrounding interstellar medium. This feedback process can regulate star formation by either compressing gas clouds to trigger new star birth or dispersing gas and preventing further star formation. In extreme cases, multiple supernovae can create superbubbles, vast cavities in galaxies filled with hot, ionized gas. The Milky Way itself has been shaped by countless supernovae over billions of years. Some astronomers suspect that past supernova explosions may have influenced the evolution of life on Earth. The hypothesis of a supernova-induced mass extinction suggests that cosmic rays from a nearby explosion could have altered Earth's atmosphere, leading to climate change or increased mutation rates. While no definitive evidence links a supernova to past extinctions, isotopic traces of iron-60 found in deep-sea sediments suggest that at least one supernova occurred relatively close to Earth within the last few million years. The search for supernovae extends beyond our own galaxy. Astronomers regularly discover and analyze supernovae in distant galaxies, using powerful telescopes like the James Webb Space Telescope. These extragalactic supernovae provide crucial data for understanding the early universe, as they offer glimpses into the lives and deaths of the first generations of stars. Some of the earliest supernovae may have contributed to the reionization of the universe, a period when the first stars and galaxies transformed the cosmos from a dark, neutral state into the bright, structured universe we see today. The interplay between supernovae and cosmic rays is another fascinating area of research. Supernova remnants, like the famous Tycho and Cassiopeia A remnants, are believed to be primary accelerators of cosmic rays, high-energy particles that travel near the speed of light. When these charged particles collide with the interstellar medium, they produce gamma rays, which can be detected by space telescopes. Understanding the origins of cosmic rays could shed light on some of the most energetic processes in the universe. In recent years, astronomers have begun using machine learning and artificial intelligence to detect and classify supernovae more efficiently. Automated surveys like the Zwicky Transient Facility, ZTF, and the upcoming Legacy Survey of Space and Time, LSST, are expected to discover thousands of new supernovae every year. These vast datasets will help refine theoretical models and potentially uncover new, exotic types of stellar explosions that defy current classification. Another breakthrough in supernova studies came with the advent of gravitational wave astronomy. When two neutron stars collide, a process often initiated by a supernova, they produce both a visible explosion, called a kilonova, and gravitational waves, ripples in spacetime first predicted by Einstein. The detection of gravitational waves from the neutron-star merger GW170817 confirmed that kilonovae are responsible for creating heavy elements like gold and platinum, solving a long-standing astrophysical mystery. As technology advances, astronomers hope to capture a supernova in the earliest stages of its explosion, something that has rarely been observed in real time. Supernova early warning systems, which monitor nearby stars for pre-explosion activity, may soon allow scientists to predict and study these stellar deaths as they unfold. If successful, such efforts could provide unprecedented insights into the final moments of massive stars. Even in death, supernovae continue to shape the universe in ways we are only beginning to understand. Their explosive legacies live on in the stars that form from their remnants, in the elements that compose planets and life itself, and in the mysteries they leave for future generations to explore. Supernovae are not just violent endings, they are also cosmic rebirths, setting the stage for the next generation of stars, planets, and even life. The elements forged in these titanic explosions, carbon, oxygen, silicon, iron, and countless others, become the building blocks of everything we see around us. Every atom in our bodies heavier than hydrogen and helium was, at some point, created in the heart of a massive star and released into space by a supernova. In this sense, we are all made of stardust. One of the most enigmatic consequences of supernovae is the creation of exotic objects like quark stars, a hypothetical state of matter even denser than neutron stars. Some physicists speculate that under extreme pressure, neutrons in a collapsed star could break down into their constituent quarks, forming an incredibly compact remnant. While no confirmed quark stars have been observed, ongoing studies of unusually massive neutron stars suggest that these strange objects might exist. Supernovae are also responsible for some of the most luminous transient events in the cosmos. One such phenomenon is the parainstability supernova, a rare explosion that occurs in extremely massive stars, at least 150 times the mass of the Sun. Unlike typical core-collapse supernovae, which leave behind a remnant, parainstability supernovae completely annihilate the star, leaving no black hole or neutron star behind. These colossal explosions were likely more common in the early universe when massive first-generation stars dominated. Another fascinating class of explosions is the so-called zombie or repeating supernova. Some supernovae, like the peculiar IPTF-14HLS, have defied expectations by exploding multiple times over several years instead of fading away. This challenges existing models of stellar death and suggests that some massive stars may undergo prolonged, episodic eruptions before finally collapsing for good. Supernova remnants, though often associated with destruction, can also be sites of intense astrophysical activity. Pulsar wind nebulae, for instance, form when a rapidly spinning neutron star, or pulsar, injects high-energy particles into its surrounding environment. One of the most famous examples is the Crab Nebula, which houses a central pulsar that rotates 30 times per second, emitting beams of radiation that sweep across space like a cosmic lighthouse. The effects of supernovae extend far beyond their immediate surroundings. Some researchers believe that the cosmic rays generated by supernovae may have influenced Earth's climate over geological timescales. The hypothesis, known as the cosmic ray climate connection, suggests that variations in supernova activity in our galactic neighborhood could affect cloud formation and, consequently, global temperatures. If true, this would mean that the history of life on Earth has been subtly shaped by distant stellar explosions. From a technological standpoint, the study of supernovae has led to innovations that extend beyond astrophysics. The techniques developed to detect and analyze supernovae, such as advanced image processing, machine learning, and high-energy particle detection, have applications in medical imaging, nuclear physics, and even materials science. The hunt for neutrinos from supernovae has also inspired the construction of massive underground detectors, which are now used for monitoring nuclear activity and searching for rare particle interactions. Looking forward, astronomers are eagerly anticipating the next nearby supernova, as it would provide an unprecedented opportunity to study these cosmic explosions up close. Some candidates, like Betelgeuse and Eta Carinae, are closely monitored for signs of impending collapse. When the next supernova occurs in the Milky Way, it will not only be a spectacular sight but also a moment of scientific discovery, potentially answering long-standing questions about stellar evolution, nucleosynthesis, and the nature of extreme matter. As we peer deeper into the universe with increasingly sophisticated telescopes, we continue to uncover new mysteries about these celestial explosions. Each supernova, whether a fiery death or a rebirth of cosmic matter, tells a story of transformation, destruction, and creation, a cycle that has shaped the universe for billions of years and will continue to do so for eons to come. Supernovae are also key players in the cosmic web, the vast structure of galaxies, filaments, and voids that define the large-scale architecture of the universe. When a supernova explodes, it not only enriches its host galaxy with heavy elements but also injects immense kinetic energy into the interstellar medium. This energy influences star formation rates and can even drive galactic winds, powerful outflows of gas that regulate a galaxy's growth and evolution. In extreme cases, these winds may strip galaxies of their star-forming material entirely, leading to the eventual death of a galaxy. Some of the most puzzling supernovae are those associated with gamma-ray bursts, GRBs, the most energetic explosions known. Long-duration GRBs are thought to arise from the deaths of particularly massive stars, where the collapsing core forms a rapidly spinning black hole. This process generates twin jets of relativistic plasma that pierce through the dying star, releasing an immense burst of gamma rays detectable across billions of light-years. GRBs are so powerful that a single event can briefly outshine all the stars in its host galaxy combined. Scientists are still unraveling the precise mechanisms behind these extreme events and their role in shaping the universe. Another fascinating phenomenon linked to supernovae is the presence of runaway stars. These are high-velocity stars that have been ejected from their home systems due to a supernova explosion. When a massive star in a binary system explodes, the sudden loss of mass can send its surviving companion hurtling through space at incredible speeds. Some runaway stars are traveling so fast that they may eventually escape the Milky Way entirely, becoming intergalactic wanderers. Supernovae also play a crucial role in one of the biggest mysteries in cosmology, dark energy. Observations of Type Ia supernovae in distant galaxies revealed that the universe's expansion is not slowing down due to gravity but is instead accelerating. This groundbreaking discovery, which earned the 2011 Nobel Prize in Physics, suggested the existence of dark energy, an unknown force that makes up roughly 70% of the universe. Without supernovae acting as cosmic mileposts, this revelation about the fundamental nature of the cosmos might never have been made. Even within our own solar system, evidence of past supernovae can be found. Scientists have discovered traces of iron-60, an isotope produced in supernovae, embedded in Earth's deep-sea sediments, on the Moon, and even in Antarctic ice. These findings suggest that one or more nearby supernovae may have occurred within the last few million years, possibly influencing Earth's environment in subtle ways. Some researchers speculate that these explosions may have contributed to evolutionary changes by increasing mutation rates or altering atmospheric chemistry. The future of supernova research is brighter than ever. Upcoming space missions, such as the Nancy Grace Roman Space Telescope, will survey the sky for new supernovae, helping refine our understanding of dark energy and the expansion of the universe. Meanwhile, ground-based observatories like the Extremely Large Telescope (ELT) will allow astronomers to study supernova progenitors in unprecedented detail, potentially identifying stars on the brink of explosion before they go supernova. One of the most ambitious projects in astrophysics today is the effort to detect a supernova in real time from its earliest moments. By monitoring massive stars with space-based observatories and neutrino detectors, scientists hope to catch the very first signals of a supernova, before the explosion even becomes visible. This would allow for an unparalleled observational campaign, capturing every stage of the event as it unfolds. Supernovae are reminders that the universe is dynamic, ever-changing, and interconnected in ways we are only beginning to grasp. From their role in forging the elements that make up planets and life to their influence on the evolution of galaxies and the expansion of the cosmos, these stellar explosions are among the most important and awe-inspiring phenomena in nature. The next supernova could be discovered at any moment, and when it does, it will undoubtedly bring new insights into the workings of the universe. Supernovae are also linked to some of the most extreme astrophysical environments in the universe, including accretion disks around black holes and the violent interactions within dense star clusters. When a supernova occurs in a crowded stellar environment, such as a globular cluster or the core of a galaxy, the energy released can disrupt surrounding stars, trigger new waves of star formation, or even influence the motion of nearby black holes. Some astronomers believe that repeated supernova explosions in the centers of galaxies may play a role in feeding the supermassive black holes that reside there, providing them with the matter needed to grow. Another intriguing connection between supernovae and black holes comes from the study of so-called fallback supernovae. In these cases, the initial explosion is not strong enough to fully eject the star's outer layers, causing some of the material to fall back onto the collapsed core. This process can lead to the formation of a black hole rather than a neutron star and may explain why some black holes appear to be born with unexpectedly high masses. The study of fallback accretion is helping astrophysicists understand the distribution of black hole masses and the conditions under which they form. Beyond individual stars and galaxies, supernovae may also have had profound effects on the early universe itself. During the first few 100 million years after the Big Bang, the universe was filled with primordial hydrogen and helium, with little to no heavier elements. The first generations of supernovae, originating from massive population 3 stars, were responsible for producing the first heavy elements, fundamentally altering the composition of the cosmos. Without these early supernovae, later generations of stars, capable of forming planetary systems and eventually life, would never have been possible. Interestingly, supernovae may also act as natural laboratories for testing the fundamental laws of physics. The extreme conditions inside an exploding star push the boundaries of our understanding of nuclear physics, particle interactions, and even the behavior of gravity under extreme densities. For example, the study of neutrinos from supernovae provides insights into weak nuclear interactions, while observations of supernova remnants offer constraints on alternative theories of gravity that go beyond Einstein's general relativity. One of the most exciting developments in modern astrophysics is the growing capability to study supernovae across multiple wavelengths and messengers. Traditionally, supernovae were studied using visible light, but today, astronomers also observe them in X-rays, gamma rays, radio waves, and even through gravitational waves and neutrinos. This multi-messenger approach allows for a more complete picture of the explosion, revealing details about the supernova structure, the nature of its progenitor star, and the dynamics of the surrounding environment. For example, Some supernovae produce powerful radio emissions long after the explosion has faded from visible light. These radio signals provide clues about the interaction between the supernova ejecta and the surrounding interstellar medium. In some cases, they reveal the presence of dense, previously undetected stellar winds or companion stars that shaped the explosion. Similarly, infrared observations are crucial for studying supernovae hidden behind thick clouds of dust, which would otherwise remain invisible to optical telescopes. The role of supernovae in planetary system formation is another area of active research. Some scientists believe that shockwaves from nearby supernovae may have triggered the collapse of the molecular cloud that eventually formed our solar system. Isotopic anomalies in meteorites, particularly the presence of short-lived radioactive isotopes like aluminum-26, suggest that a supernova explosion may have enriched the early solar nebula, influencing the chemical composition of the planets and potentially even playing a role in the conditions that led to life on Earth. Looking even further into the future, some researchers speculate about the eventual fate of supernovae in an aging universe. As star formation slows down over cosmic timescales, the rate of supernovae will decline as well. However, even in a far future universe dominated by long-lived, low-mass stars, some forms of stellar explosions may still occur. White dwarf mergers, for instance, could continue producing Type Ia supernovae for trillions of years, providing one of the last sources of energy and illumination in an increasingly dark and quiet cosmos. Despite all that we have learned, supernovae continue to surprise astronomers with unexpected behaviors and exotic variations. Some stars defy predictions by exploding at lower or higher masses than expected, while others produce unusual light curves that challenge existing models. The discovery of new classes of supernova-like explosions, such as fast blue optical transients, FBOTs, and calcium-rich transients, suggests that our understanding of stellar deaths is still incomplete. Each new supernova observed adds another piece to the puzzle, helping refine our knowledge of how stars live and die. The study of supernovae is not merely an academic pursuit, it has profound implications for our understanding of the universe and our place within it. From the origins of elements to the fate of galaxies, from the mysteries of dark energy to the physics of extreme matter, these stellar explosions hold the keys to some of the biggest questions in science. As new telescopes, detectors, and technologies come online, the next generation of astronomers will continue uncovering the secrets hidden within these cosmic firestorms, ensuring that the story of supernovae is far from over. Supernovae also serve as cosmic time capsules, preserving information about the physical conditions of the universe at different epochs. By studying the remnants of past explosions, astronomers can reconstruct details about the environment in which these stars lived and died. In some cases, supernova remnants contain traces of interactions with dark matter, offering a potential observational window into one of the greatest mysteries in modern physics. One of the most fascinating and poorly understood aspects of supernovae is their potential connection to fast radio bursts, FRBs. These mysterious millisecond-long bursts of radio waves originate from distant galaxies and often appear to be linked to magnetars, which are themselves the remnants of core-collapse supernovae. Some scientists propose that certain FRBs may be caused